Alright, today we're gonna pull back the curtain on some seriously cool invisible engineering. You know, the kind that lets architects build those huge, wide open spaces we see everywhere? The secret that basically lets concrete defy gravity over some truly incredible distances.
So let's just start with a really simple question, something that gets right to the heart of modern design. Think about it. You walk into a massive parking garage or one of those super trendy open plan offices, and you look up. You see this gigantic ceiling, but where are all the columns? How is all that weight being held up? It almost feels like it's breaking the rules of construction, right?
Okay, here's how we're gonna break it down. First, we'll look at the big problem with concrete. Then, we'll get into the super clever solution and its two, let's call them secret weapons. And finally, we'll see the amazing things you can build because of it.
All right, first up, the concrete conundrum. Let's really dig into the biggest challenge you face when you're working with a plain old concrete beam.
So just picture a simple, straight concrete beam, right? It's just sitting there, stretching between two columns. And yeah, it looks super solid, super reliable, and in a lot of ways it is. See, concrete is an absolute beast when you compress it, when you squeeze it from both ends. It loves that.
But, and this is a big but, here's the problem. Just from its own massive weight, we're not even talking about adding cars or people or anything yet, that beam starts to bend. It sags right in the middle. And the longer you make that beam, the worse that sag gets.
So this sagging has a technical name. It's called deflection. And here's why it's such a big deal. As that beam bends, think about what's happening to the bottom edge. It's getting stretched apart, right? That stretching force is called tension. And tension, well, that is concrete's kryptonite. It's the one thing it's really, really bad at handling. And that weakness can lead to tiny cracks, which can lead to big problems.
So, what do you do about this fundamental problem?
Well, the solution is it's so clever and almost deceptively simple. The idea is you fight that bend before it even has a chance to start.
Okay, so here's what engineers do. They add a new player to the game. Inside the concrete, they place a special duct. And inside that duct is a cable made of super high-strength steel strands. We call this whole thing a tendon. And I mean, this is not your average steel. This stuff is about 3 times stronger than the normal rebar you might have seen at a construction site.
But the real genius here, the absolute key to everything, is its shape. This tendon isn't just laid in there straight, no way. It's carefully threaded through the beam in a very specific curve. It swoops down low right in the middle, and then it curves back up high over the columns. If you look at it, it's basically the exact opposite shape of that natural sag we were just talking about. It's a perfect mirror image.
Okay, now for the fun part. The concrete gets poured and hardens all around this curved tendon. And then, the magic happens. Let's get into exactly how that specific curve creates this amazing upward push. So once that concrete is rock solid, a massive hydraulic jack comes in, grabs the ends of that steel tendon, and pulls, really pulls, with incredible force. Now think about it, that super strong steel cable is now under massive tension. And what does it want to do? It wants to be perfectly straight, but it can't because it's trapped inside that curved duct in the concrete. So its desperate attempt to straighten out forces it to push upwards in the middle of the beam, and this creates a constant, powerful upward lift from the inside out.
And that upward force has a name. Engineers call it the balance load. And that's exactly what it does. It's literally like the tendon is lifting the beam from the inside, balancing out the downward pull of gravity and any weight you put on top of it. This is how you can have these super long spans without any of that dreaded sagging.
But wait, there's more. Seriously. That upward lift is brilliant, but it's only half the story. Post-tensioning has another secret weapon that actually makes the concrete itself way, way stronger.
And this brings us to what I like to call the squeeze play. It's all about compression. There's a great analogy for this. Try to pick up a row of books just by lifting from the bottom. They'll all just fall apart, right? But what if you squeeze them really hard from both ends? Suddenly, you can lift the whole stack. They act like one single solid block.
Well, that's exactly what's happening in our concrete beam. Remember how that tendon is anchored at both ends? When the jack pulls it tight, it's not just creating that upward lift, it's also squeezing the entire beam from end to end, just like you squeeze those books. The whole thing is put into a constant state of high compression.
And this constant squeeze is just awesome. For one, it stops those little shrinkage cracks from even forming while the concrete is drying. But more importantly, it gives the beam incredible strength against bending. Remember how we said tension is concrete's big weakness? Well now, before the bottom of the beam can even start to feel any of that dangerous stretching or tension, it first has to fight through and overcome all of that powerful compression we've squeezed into it. It's like giving it a superpower.
Okay, so let's put it all together. You've got this upward lift from the curved tendon, and you've got this powerful internal squeeze from the compression. What does that actually mean? What can we build now that we couldn't before?
Well, here's the payoff, plain and simple. When you compare it to a standard concrete beam, the difference is huge. A post-tension beam can be way thinner and lighter, and because it's actively fighting gravity and is pre-squeezed to be super strong, it can span much longer distances with minimal sag. And it's way more durable because you've basically eliminated the cracking problem. It all works together to let you build those huge open spaces we started with.
So at the end of the day, this is the technology that unlocks so much of the architecture we just take for granted. You know those incredibly long open spans in a parking garage? The huge column-free floors in office buildings? Even those sleek, skinny-looking bridges? Yep, it's all thanks to this super elegant engineering trick.
And that's the secret. It's this brilliant two-part system. You fight the sag with a built-in upward lift, and you fight the weakness of tension with a powerful constant squeeze. So, the next time you're walking through one of those massive, wide-open buildings, and you find yourself wondering, how in the world is this whole thing staying up? Now you'll know. The answer isn't just in the columns you can see, it's in the invisible, superpowered strength working away deep inside the concrete itself.